All right, so for lesson 72, we're going to start off with factors that are sums, making sure we understand that concept. And it looks a little weird the first time you see it, but it's not really a new concept. We've done this before. So, like if I have 2x plus 4, let me do it like this. Let's do 2x squared plus 4x. What values are common to both of those terms? In other words, what value can I factor out of both of those terms? This is the point at which you can get your name on the board. 2. So a 2 can come out here. Both of them are divisible by 2. So, yep. Is there anything else? What'd you say? One of the x's, right? So both of them have an x, so I can factor that out as well, right? So if I do that, then I'm left, what times 2x will give me x squared? Well, 2x times x will give me x squared. And 2x times 2 will give me 4x, right? So I can factor it out and simplify it that way, all right? So we've done that before, and what we're about to do is the exact same idea. It just looks a little more complicated because the things that we're factoring out now are going to look like this. We're going to factor out terms that are added together, factor out sums. All right, so let's look at this for example. A plus b times x squared minus a plus b times x minus 6 times a plus b. So when we look at this and we look at all the different terms that are in there, we need to recognize that there are actually 3 terms, right, that are connected by these minus signs right here. So that's the first thing to recognize. Don't get confused by the plus signs that are in here. Those are all part of these same terms that are bigger terms, right, that are connected by these minus signs here. So if we think about it that way, what can we factor out? What's common to all 3 of these terms? What do all of them have? A plus b, right? Does everybody see that? So we can factor out an a plus b from all of these terms, and when we do that, we're left with an x squared right here. We're left with a minus x right here, and we're left with a minus 6 right here. So that would be that problem factored, right? Factoring, you're pulling out everything that's common. That one should hopefully be pretty simple to see. Does that make sense to everybody? So now let's do one that's not quite, maybe a little bit harder to see. So if we have x minus 1 times x squared plus 7mx times x minus 1 plus 10m times x minus 1. Right, so looking at this problem, what would you say is common to every term that's in there? Again, we got to make sure we identify the terms. These are the terms because they're the ones connected by the plus signs there. All right, so we got 3 terms in here. What would you say is common in each of those terms? X minus 1, absolutely. They all have an x minus 1. Is there anything else that you see that all of them have? They all have an m as well, right? If this one down here had an x hanging off the end, we could say they all had an x as well, but they don't. That last one didn't have an x. So they all have an x minus 1, and they all have an m, right? So we're going to take that, and we're going to multiply it times the terms that would be left if we factored all of those pieces out. So what would be left in this term if we factored out, the first term, if we factored out an m times x minus 1? X, just x squared, right? And then for the next one? Just 7x, right? And then finally for the last one, it's just 10, right? Does that make sense to everybody? Now, are these problems complete? Have we factored as far as we can for these two? Do you guys see that in both cases, when we factored out the stuff that was common to them, that what was left on this side here, that the three terms that were left, it's basically a trinomial like we learned how to factor last time, right? So for both of these, we can actually factor the trinomial further. So we can say a plus b is going to be times two binomials with x's as the first term. And what would go here and here for this one when we factor? Are we looking at 1 and 6 or 2 and 3 for the factors of 6? 2 and 3, right? Because we've got to have something that's going to equal a negative sign here. So it's either going to be -2 and +3 or +2 and -3. And when you add those together, they've got to equal a -1. So which one does it need to be? -2 +3 or -3 +2? Did you say -2?
-2
Negative. So let's just try that. Let's think about our little thing that I showed you guys a minute ago. So let's say -2 +3. -2 times 3 gives us our -6, like we need. -2 plus a +3 gives us a +1. Oh, so we need a -1, right? So you're close. We just need to reverse the sign. So let's make this a +2 and a -3. And then we'll get the -1 there. So +2 -3. Make sense? And we can do the same thing over here. M times x plus 1. Somebody nod on the board, want to tell me what my factors would be for this guy? We're looking for factors of 10 that when multiplied together give us a +10, and when added together give us a +7.
2 and 5.
2 and 5. +2 and +5 will do that, right? Is the factoring stuff starting to click with you guys? Factoring trinomials? Good. Once you get it down, it's pretty simple. It's just, you've never seen it before. It's like, what? What just happened? All right. So that's factoring. That's how you factor sums. What it means by factoring sums is these things are sums, right? A plus b, a plus b, a plus b. We factored those sums out. Now let's talk about pyramids and cones. And they've got a whole bunch of different drawings on, like if you look on page 292 and you look on page 293, a bunch of different drawings for cones and pyramids, and they show some that are slanted. This chapter, we're not really worried about the like the slanted pyramid that's at the bottom of page 292, or the slanted cone that's at the bottom of page 293. Sorry, we're going to be looking at right pyramids and right cones. And when we say right, what we mean is that if you draw a dotted line through the middle of it, right? I should have drawn my cone part first. I'm going to circle at the bottom first. But when you look through, when you draw a line up to the top, it's going to form a right angle with the bottom. So that's what we mean by right pyramids, or right circular cones, or right pyramids. And so that's what these questions are all about. We're looking at the right ones, and they're going to ask us about we need to be able to calculate the volume, and we need to be able to calculate the surface area with these guys. All right? So let's start with volume. The volume for both the pyramid and the cone is the same. And so volume of pyramid or cone is equal to, B is equal to 1/3 the area of the base times the height. So you write that as, I've seen it different ways. I tend to write it like this, the area of the base times the height, but I've seen some books where they use 1/3 times, and they use a capital B here to signify the area of the base times the height. The important thing is that you understand that that means 1/3 the area of base times the height, all right? Whatever symbol you want to use to signify that. But we're talking about the area, in this case here, the area of the circle times this height here, right? From the bottom of the figure to the top. All right, so let's just do a quick example for this one here. Let's say that we said the height of this guy was 5 inches, all right? And we said that the radius right here, and we'll just do the whole diameter. We'll say the diameter of the bottom here is 4 inches, all right? So if that was the case, how would I calculate the volume of this cone? The volume of the cone is 1/3 the area of the base. So what would the area of the base of this guy be? What's the area of a circle? What's the formula for that? And this is one that it's in your book. You can look it up in your book, but it's one that you need to commit to memory. The area of a circle.
Pi times the radius squared.
Pi times pi r squared, right? Pi times the radius squared. So we're going to do pi. What's our radius for this guy? For this circle?
2.
It's 2, right? So we need to understand what I gave you here was the diameter. We need to take half of that to get the radius. So pi, I'm just going to write down pi r squared times h is what we're trying to find. So we're doing 1/3 pi times 2 squared times our height, and our height's given as 5, right? So times 5. So we simplify that further. We have 1/3 pi times 4 times 5, or we could write that as 1/3 20 pi. And then when we multiply through by the 1/3, sometimes you'll see the answer with pi left in there. So it'd be 20/3 pi. What would our units be on that? Is it just inches? What you need to recognize is when you calculated the area here, and you did pi r squared, when you did pi times pi times 2 inches squared, you got an answer that was 4 pi inches squared, because you had to square the inches too. And then when you multiplied it times the 5 inches, that was right here, you take that and you multiply it times the 5 inches, it actually is going to give you a unit of inches cubed. All right, so volume will always have a cubic unit. So 20/3 pi inches cubed would be our units for that. And then we can punch that in the calculator and just use 3.14 as our value for pi. And whoops, I don't have let me get a calculator. If I punch that into my calculator, I get 20 divided by 3 is 6.666666 times 3.14. So I get a value of 20.9 if I round it to 1 decimal place. So either of these answers would have been correct, and as you're checking it with the back of the book, you may see one or the other. Does that make sense to everybody? See how we did that? Now, what if we we're asked for the volume, but this time we're asked for the volume of a pyramid, and we're told that this pyramid looks like this, then we got sides that are coming up here to this point, And I probably should have drawn like dotted lines here. This is behind the pyramid. That's a dotted line, and this is a dotted line here, right? And we're told that it has a square bottom on it that's 6. I'll just do 6 feet, all right? And then we're told that there's a height here. The height of our pyramid is 5 feet. All right? And like I said, it's square, so this is 6 feet over here as well. How would I find the volume of that? The volume for both of these are the same in that it's the volume equals the area of the base, right, times the height. But how you calculate the area of that base is different, right? What's the area of this base? What's the area of a square? So it's an easy way for one of you guys that are on the board to get on the board. You guys remember seeing a drawing like this where you had a square and it said the length of the side was S, and so A is equal to S squared? Right? Or you can think of it as you know, both sides are S, you can kind of think about it like you do a rectangle where you have length and width, and so you say area is length times width. And so if you say S times S, you get S squared also. Right? So the area of the base would just be 6 times 6. Then we're going to multiply that times the height, which is 5. So we have 36 times 5, and I don't know what that equals off the top of my head. 180? 180. 180, and again, our units are cubed, so 180 feet cubed would be our answer for that. All right, you guys good with that? Yep. Yeah. So let's talk about surface area. Let's move on from there, from considering volume, just talking about surface area. And for surface area, for these shapes, you need to know not this height right here, right? Not this H that's a line drawn up from the middle, but you need to know what we refer to as the slant height. And the slant height is this distance right here. Okay? And with slant height, we use the letter, just because we want to be confusing, we're going to use the cursive letter L, which is exactly what I used over here for the length of the rectangle. All right, but that has a slant height, and same thing here, right? There's a height that's the 90 degrees from the middle, but then there's also this slant height, which is the distance if you measure from the bottom of a side up to the top of the side. You guys see the distinction between that? Right, our 5 feet here is actually like we have put a dot in the middle. That's our 5 feet. It's kind of hard to draw with this figure, but it's that perpendicular line going straight up there, that distance. Whereas the other one is the distance on the side. Okay? And so, you guys familiar with the Pythagorean theorem? Have we used that in here yet? Pythagorean? Maybe not? Maybe? I can't remember. Let me just see. Surely we cover it in here. Pythagorean theorem 407 and 409. So no, we're not there yet. All right, so I'm not gonna go there. We're gonna eventually figure out if they gave us the height and we didn't know the slant height, we're gonna figure out how we can calculate that. But for now, for these problems, they'll give us the slant height. All right. So let's say we said that this distance here, instead of the 5 feet being this height here, let's say we said the 5 feet was actually the slant height. All right. So this equals 5 feet. And so we were asked to find the surface area of this guy. What do I mean by surface area? Do you guys know? Like if I asked you to find the surface area of this board, because the board's basically flat, we're just talking about the area of this rectangle that is represented by the board, right? So this is like, I don't know, 4 feet by 6 feet. So it'd be 4 times 6, it'd be 24 feet squared would be the surface area of the flat board, right? But when you're dealing with something that's not flat, you have to basically take the area of all the different faces and add them all together. All right, so if we want the surface area of this, and since this is a 4-sided pyramid, we need the area of each face as well as the area of the base. Does that make sense to everybody? All right, so the slant height is what's going to allow us to find the area of each of the faces. Because now that we know the slant height, basically each face has a height of 5 feet and it has a base of 6 feet, right? And we know how to find the area of a triangle if we know the height, right? If we know this perpendicular distance here, and we know the base. What's the area of a triangle like that? What is it? Not gonna try it? Nobody else knows. You may be the one that knows. What's the area of a triangle like this? Half of base times height, exactly. So some of you think of this as 1/2 BH. Some of you think of it as BH over 2. Both is true, it's the same thing, right? And so when we plug that in, we get 1/2 of 6 times 5, or 1/2 of 30, so it's gonna be 15 feet squared, right? So that's the area of one of these faces on our pyramid here, right? How many faces do we have? It's a 4-sided pyramid, so we got 4 faces, right? So if we're going to calculate the surface area of all these faces right here, then we have to, so total area of faces is going to be equal to 4 times 15, or 60 feet squared, all right? So surface area is equals area of faces plus the area of the base. All right? And what's the area of the base on this guy? We calculated that in the last problem. It's just 6 times 6, right? Area of base equals 6 times 6 equals 36 feet squared. So then we take the area of the faces, which we said was 60, and we add that to the 36, which is the area of the base, and so we get an overall surface area of 96 feet squared. So you have to do, for the pyramid, you just add up the areas of each of the faces. Okay? We're going to need a separate formula. So for this one, we were using shapes and areas that we were already familiar with. We're going to need a separate formula to find the surface area of a right circular cone. And so the formula for that is that we know how to find the area of the base, right? The area of the base is just the area of a circle, which you're familiar with. That's pi r squared. But so surface area for this is still the what we call the lateral surface area. The lateral surface area is what I was called the area of the faces before, right? It's the area of the stuff around an object, not counting its base and if it's got a top, the top. You don't count the base and the top. It's just the stuff around the outside. So like on a roll of paper towels, right? The lateral surface area would just be the surface area where the paper towels are. You wouldn't count the top and the bottom. So in a figure like this, the lateral surface area is just all of this stuff here, not including the base. All right? And that was the same thing for the pyramid that we had a minute ago. The lateral surface area was just those faces, but not counting the base. All right? So surface area is always the lateral surface area plus the area of the base. Plus the area of the top, if you have a top. On these figures, we don't. And so what you don't know how to calculate is the lateral surface area of this cone. So I'm going to have to give you a formula for that. So lateral surface area of cone equals pi RL. All right, so pi times the radius of our circle down here times the slant height that we give you in the problem. Okay? So this is radius, and this is the slant height. And that's just a formula you're going to have to know. All right? You have to memorize that one. You'll have some problems to help you get it stuck in your head. All right? So then now that we know all of that, if we're told, for example, that the slant height for this guy is, let's say that we're told that this is 6 inches, then we should be able to calculate the surface area of this cone. Because it's the lateral surface area, which is pi RL, plus the area of the base, which we said was pi r squared. All right, surface area of cone is going to be that. Pi r times the slant height plus pi r squared. Does that make sense to you guys? You guys follow me there? So pi r squared, pi, r is 2, L is 6, plus pi 2 squared. So those are the numbers that we're actually plugging into our calculator. We get a 12 pi here. We get a 4 pi here. 12 pi plus 4 pi is 16 pi. It's area, not volume. What's our unit for area? Will they be square units, cube units, just the unit? What will it be for area? Huh? Huh?
Just the unit.
No, it won't be just the unit because we're like, if you think about when we found the area of our circle down here, we squared the inches. And so area is always a square unit, all right? It's always going to be whatever our base unit is squared. So inches squared, all right? But you participated well, so that counts. Does that make sense? Volume will always be cubed, area will always be squared, and then if you're just finding like the length or the width, it's just going to be the unit, the base unit. Okay? All right, any questions about this? I spent way longer on that than I thought it was going to take me. Let's move on to lesson 73, where we're going to do factoring of 2 squares. So this one should go pretty fast. We've learned how to factor. Trinomials. So lesson 73. We know how to factor trinomials. We know how to do something like this. That, right? We can just say this is x minus 3 plus 2. We've done that. But sometimes you'll see a problem that looks like this. And you're like, well, I'm not sure. Well, actually, you do know how to do this. If you think about this trinomial like this, x squared plus 0x minus 9. Did you guys do that? can factor that, right? You would say that's x, x. The factors, we're going to have to use the factors of 3. All right, 3 times 3, not 9 times 1. And so does everybody see that if I did a minus 3 and a plus 3 here, negative 3 times positive 3 gives me the negative 9, and negative 3 plus a 3 gives me the 0. So that would be that factor. And turns out that if you, this will always be the case if these two terms right here, well, I mean, not include the minus. If these two terms right here, these two numbers right here are perfect squares. 9 is a perfect square. So if that was 4 on the end, or 9, or 16, or 25, and there's a minus sign in front of it, then we call this right here, where you have a perfect square here and a perfect square here with a minus sign in between it, we call that the difference of two squares. And so if you recognize that, difference is what the subtraction part is, right? If you recognize that it's the difference of two squares, then the answer will always be the square root of the first term, right? The square root of x squared is x, so those square roots there. The square root of the second term, square root of 9 is 3. And then for your signs, you just put alternating signs in the middle. Pretty easy, right? Simple, we're done. So I mean, I could also give you something like this. If I said 4x squared minus 25. You look at that and you're like, 4x squared is a perfect squared. The square root of 4x squared is what?
2x.
2x. Square root of 25 is 5. And so I just say, oh, no problem. 2x, 2x, 5, 5. And put alternating signs in the middle. And I'm done. All right, so the only trick to this is just making sure you recognize that it's the difference of two squares. Okay? That's pretty simple, right? You guys agree? Good. I was hoping you would. Let's talk about probability without replacement. So last week we discussed, we have 10 marbles, 5 are red, 5 are blue. What's the probability that I'll pick a blue marble twice? So we picked a blue marble out, but then we put the blue marble back in. So we said the probability in that case, if you're replacing the blue marble, the probability of blue twice, since we're replacing the marble each time, what's the probability of me picking a blue marble the first time? How did we figure out that probability? Remember for the single choice, probability is number of desired outcomes divided by the number of possible outcomes. So we've got a bag full of 10 marbles, half are blue, half are red. What's the probability of me picking one blue? Well, there's 5 that are blue, so my desired outcome in that case would be 5, right? And the possible outcomes, there's a total of 10 marbles, so the possible outcomes is 10, so my total probability there would be 1/2, right? So I said, what's the probability of picking blue twice? If I'm putting the marble back, what's the chance that I'll pick the blue the second time? It's going to be 1/2 again, right? I've got 5 blues and 5 reds again, so it's 1/2 times 1/2. So with replacement, the probability with replacement is 1/2 times 1/2, which equals 1/4. All right? But now what if I don't put the blue marble back? Does everybody see that if I don't put the blue marble back, this first probability is going to be the same, but I've changed the conditions for the second probability, right? So if I do the probability of blue twice, and this one's without replacement, then the first time it's the 1/2, but the second time, if I kept the blue the first time, I've got one less blue the second time. Does everybody see that? So my P for the second time is going to be only 4 blues that I can choose from. And what's my total number of marbles? Is it 10? I kept 1, so it's 9 now, right? So it's 4 divided by 9 is the probability of the second one. So the probability of picking the blue twice is going to be 1/2 times 4 times 9. All right? So the total probability of this guy would be 4 divided by 18, which I could simplify to be 2/9. All right? So that would be, this is the probability with replacement. I spelled that wrong. With replacement. And this is the probability without replacement. Okay? It really hasn't changed much. It's just we have to understand that the conditions are a little different the second time. Is that cool? All right, last thing. Scientific notation. You guys done that before? I hope. Who's seen scientific notation before? Okay, Cohen has. It sounds familiar. All right. It's pretty simple. It's just you got to make sure that you don't get confused about what to do with the decimal, which direction to move the decimal. All right. So you guys will have some sample problems to kind of practice this. But with scientific notation, this is a number in scientific notation. It looks like that. Right? Or it could look like that. The exponent on the 10 could be a positive or a negative number. You're always going to have some number in the front here times 10 to some power. This number in the front, in proper scientific notation, this number in the front here has always got to have just one number followed immediately by a decimal. Okay? And so you can never put like I couldn't have 25 times 10 to the 4th. That's not valid scientific notation. There has to be a decimal there for it to be in scientific notation. And the decimal has to come right after the first number. All right? Now, if you only had a single number there, if it was like 3 times 10 to the 8, which is the speed of sound in meters per second, that would be proper scientific notation because you don't have multiple numbers there with the 3. But if this value was 356, that would not be proper scientific notation. It would have to be written like that. Okay? So if there's a needed decimal, it's got to always come after the first number in scientific notation. Does that make sense to everybody? So what we've got to learn how to do is write things in scientific notation. So, and where scientific notation is useful is when you have really small numbers or really large numbers. All right. So, for example, let's say we have 2,396,000. All right. And I ask you to write that in scientific notation. What you're going to do is any kind of trailing zeros, you're going to remove those. So you're just going to write the part of the number that doesn't include the zeros at the end. You're going to write it like that, and you're going to put a decimal right there. Okay? Because the first part of scientific notation has to look like that, right? But this new number that I'm writing has to be equal to this. And so what I have to do is say, what multiple of 10 would I have to multiply this guy by in order to get this number here? 6. So does everybody see if I multiply this times 10 to the 6th, what that's effectively going to do, let me write it down here and put some zeros out here so we can see what's going on. What that's going to do is every time I multiply it by 10, it's going to move my decimal place one place to the right. Do you guys agree that 2.3 times 10 equals 23? Right? Each time my decimal place is going to move to the right. So each time I multiply it by 10, it's going to move to the right. So I go 1, 2, 3, 4, 5, 6. That's what I have right here. My decimal place moves all the way over there, and sure enough, I've got my original number. All right? So when you're converting a normal decimal number to scientific notation, you're trying to figure out which power of 6 do I put on, or which power of 10 do I put on here so that I'll get the original number again. All right? To me, it's a lot easier when they're positive. When it gets more confusing is when you've got 0.00000000802. All right? Now I want to write that in scientific notation. Still not hard though, because you just write that, right? You take the part that's not the zeros in the front or the end, and you write it with the decimal after the first number. And then we say, if I were to put a decimal here, how many places would I have to hop to the left to get the original number? And so I count my hops. 1, 2, 3, 4, 5, 6, 7, 8, 9. So times 10, and it's not a positive 9. A positive 9 will make it hop to the right. A negative 9 will make it hop to the left. All right, so that's how I go from a decimal number to a number in scientific notation. Does that make sense to everybody? All right, let's see if we can do the reverse. What if I gave you a number in scientific notation and I said, write 3.14 times 10 to the 5th power, write that in decimal notation. So what would you guys tell me that that would be? Is my number in decimal notation going to be bigger or smaller than 3.14? It's going to be bigger, right? We're multiplying times 10 to a positive power, so our number is going to be bigger. And the way that we're going to figure out how much bigger it is we're going to pad some zeros here. You can even put extra zeros if you want to, and just hop this guy over 5 places. All right, so it's going to be a new decimal place right there. So I write that as 3.14000. That would be 3.14 times 10 to the 5th. If it had been 3.14 times 10 to the negative 5th, I would have written my 3.14 and I would have padded it with zeros in the front. And I would have hopped over 5 places to the left. 1, 2, 3, 4, 5. And so I would have said 0.0000314. And that would be the decimal representation of 3.14 times 10 to the negative 5. Okay? The best way to get good at this is just practicing, right? The more you practice this, the more this will come easily. You just got to kind of remember to move the decimal place to the left when it's a negative power and move it to the right when it's a positive power. All right? Does that make sense to everybody? Okay, you'll have some homework problems to practice that, and we can go over it again if you have questions. Like I said, if you're struggling with some of these concepts, guys, some of you clearly, when I did the test, some of you are still struggling with certain things on the test. So please reach out and let me know, all right? Like I said, I've got limited tutor time, but I do have some tutor time available. I can send you a link to schedule that, and we can try to get that on the books and figure out what's messing you up, okay? All right, y'all have a good one.
Do you want to check?
Oh, yes, thank you.